In the previous lecture, we learned Taylor series method as well as Euler's method. So we have gone through one numerical on Euler's method as well as Taylor series method. Now let us see the second method, third method, Runge-Kutta second order method. So this is a modified version of Euler's method. So here we can see. So in case of a Euler's method, we have used this Taylor series equation. So up to third order, fourth order, first order only. So but in this case, it will be extended to second order. So you might have recall from the previous lecture. So we have truncated this up to here only. So in case of Euler's method, now it will be extended up to second order. The Runge-Kutta method is derived from the Taylor series by considering two terms. So two terms means up to second order derivative. So in case of previous method, Euler's method, we have truncated up to first order. Now we have extended this to up to second order. Replacing the second derivative with backward difference approximation. So this is the backward differential approximation. Difference approximation is incorporated here. After incorporating this and simplifying, so this equation is y into x naught. So y dash x naught h plus here y dash x naught h. This is y dash x naught h by 2 here. H get cancels. Okay, y dash x naught by 2, and again here, so for the second term, y dash x naught plus h by 2 into h. Okay, so likewise, so on simplification, you simplify this, you will get this equation. On simplification, you will get this equation. So this equation is called as modified Euler method. And it's also called as a second order Runge-Kutta method. So you don't get confused. So in the examination, they may ask it by solve using modified Euler's method or by second order Runge-Kutta method. So both are one and the same. Simply you remember. So either modified Euler's method or second order Runge-Kutta method. The second order RK method is derived by incorporating weighted average of two increments. So weighted average of two increments. So this it is equation is written also here. See, weighted average of two increments. So for example, this is the curve. So in this curve, the first point is, so this is based on x naught. Corresponding value is y naught, and the tangent at this point, so this is y dash x naught. And then the second point based on this, so we are going to find the second point, say x naught plus h, this is second interval, and corresponding y, say we will call it as a y1. So this tangent at this point, so that is y dash of x naught plus h. So this is the graphical representation. So average of these two, so this is slope plus this slope, the average of these two, so you will get slope somewhere. If you are using this for a particular point, you will get this much error. So if you are using the second derivative, you will get this much error. And if you are making average, so you will get this point somewhere in between. So such that, so we can reduce the error. So in the previous case, this is the error. So if you are taking average, so you will get this error. So likewise, so to reduce the error, so this concept is adopted, average of two increments. So this is the first increment and second increment. So the average of these two increments you will get somewhere here. So that concept is incorporated in Euler's RK method. So this is the point. Instead of getting this point value, so we'll get this. It means that this is the actual curve. So with respect to actual curve, this is the closure. So therefore, so we can reduce a error by incorporating this concept. And the similar way this can be written as, for example, this is y1. Y1 is equal to this we are representing by y0, and this term y dash of x naught by k1 and y double dash of x naught plus h by k2. So thus, so we are simply replaced by terms k1 and k2 and average of these two. Thus, where k1 is h into, so same h into y dash of x naught, h into y dash of x naught. What is the y dash of x naught? Y dash of x naught is dy by dx, dy by dx at x naught. The same, this is dy by dx. The similarly, so this is y dash of x naught plus h. So this is the derivative of this x naught plus h. So just I have shown here. So this is the slope at this point. So that can be represented by this equation. Simply what we have to do, we have to find the k1 and k2, and we know the initial boundary condition. So based on this, you can compute the new value of y1. So this concept is adapted in Euler's, Runge-Kutta method or modified Euler's method.